This is a talk called Fire and Ice, the Volcanic Worlds of the Solar System, and it's one of a series of talks that I put together and have given a number of times on cruise ships all around the world, very much aimed at the beginner level, no complicated science in this at all. It's a talk based on astronomy, but of course we're going to talk about volcanoes, and so we're going to start with a little bit of geology. If I said the word volcano, then this is perhaps what you would immediately conjure up in your mind: a cone-shaped mountain with fire bursting out of the top and molten lava, molten rock running down the outside of the slopes of the mountain. Here's another picture of a classic fire fountain volcano, this one taken in Iceland, and you've got huge eruption going on, molten lava, molten rock being thrown high into the sky, and a few fumaroles, which are little steam vents coming up at the sides of the volcano as well there. But of course, what's happening underneath is that we have a magma chamber, which is molten rock. We call molten rock magma when it's underneath the ground, and when it bursts through to the surface, we call it lava, but it's still the same thing. So that molten rock floods up into the magma chamber from deep in the core of the Earth, very high temperature, and eventually finds a way through a crack in the ground up to the surface and bursts out, and we call it lava, and it flows down the sides, and each eruption makes the cone-shaped volcano get taller and taller as the mountain builds up and the lava turns back into solid rock when it cools down. All volcanoes look like that. Here is a picture taken from space, from orbit, looking down on some mountains in Asia, and they're cone-shaped. Again, classic volcano-shaped mountains, but this one's erupting and it's not producing large amounts of red-hot lava. Instead, you can see a huge plume of ash rising high from the top of the mountain up into the stratosphere. This grey, superheated ash mixed with steam is rising out of the top of the volcano, a rather different looking eruption. So what's going on? Well, we find the volcanoes in particular places on Earth, and this picture here shows a very good illustration of that. It's called the Ring of Fire. Every little red triangle is a place where we find a volcano. And you can see they ring the outer edges of the Pacific, all down the coast of the Americas there, and all the way around Asia and down past Australia, all around the Pacific Ocean. And these are where we find, generally speaking, the ash type volcanoes. But there are some oddball cases. Right in the center of the Pacific there, we have the Hawaiian Islands, and these tend to be the lava emitting fire fountain volcanoes, and we call these hotspot volcanoes, and we'll explain the difference. For the ash volcanoes that ring the Pacific Ring of Fire, they're on the boundary between the continents and the oceans, and the Earth's surface is divided into these great plates. Some of them are ocean plates and some of them are continent carrying plates. The continents, when they bash up against and crash into the ocean plates, which are moving around the Earth, jiggling about, it causes these great collisions. But because the continents are less dense than the ocean plates, the rock in the ocean plates is saturated with water, so every last nook and cranny is filled. So they're more dense, in fact, than the continents. The continents, therefore, tend to float up over the top of them, and the ocean crust gets pushed down in a process that we call subduction. It's subducted down underneath into the core of the Earth, into the layer of magma, and is melted. And as it's melted by the immense heat deep in the Earth, all of that water that was trapped in the ocean boils as superheated steam and water and finds its way back up through the continental crust of the overlying continent along the edge, along the dividing line, and bursts out through cracks, forming these ash volcanoes. The reason it creates ash is because the superheated steam carries along with it a lot of mineral grains and dissolved minerals. And once the pressure is released, as it bursts out into the atmosphere, that dissolved mineral gets released as little mineral grains and forms the enormous cloud of ash that's projected upwards. Now, if we look at other parts of the Earth, if we look at the middle of the Atlantic, for example, we find what's called a mid-ocean ridge. This is a crack between two of the ocean plates. So the Atlantic is actually covering the two sides of two different plates of ocean crust, and they're moving apart from each other, creating this great crack in the ground where more material is coming up from deep in the earth and filling in the gap and forcing the two plates apart. And that gap in the ground comes to the surface on the island of Iceland. You can actually go and visit the crack in the ground between the American side and the European side at the Thingvellir National Park. You can walk down this pathway here, as a photograph that I took, and have your feet essentially 1 foot on the American side and 1 foot on the European side. And this gap in the ground is getting wider by about 3 centimeters every year as material is forcing its way up from underneath. Animation here that shows a ball of magma deep in the earth trying to get up through the surface, and the crack between these two plates is allowing it to come up and force its way between them, creating more rock and forcing the two ocean plates further apart. Now this acts like a giant conveyor belt, and of course we end up with enormous recycling of the Earth's crust. The ocean crust is being formed in the rising plume of magma that is at the center of the mid-Atlantic ridges, and then the two plates are pushed apart until they bump into the continents at the left and right there, where they're subducted underneath the continents and remelted, and the material then flows around through the mantle and comes back up again a couple of 100 million years later to reform new ocean plate. So in fact, no part of the ocean floor is older than about 200 to 250 million years anywhere on the Earth. Whereas the continents, which don't take part in this recycling, are where we find really ancient rocks dating right the way back to pretty much the formation of the planet, some 4,000 million years ago. So about the oldest rocks that we find on the floating continents there. Now in the center of the Pacific, there is also a rising magma plume, but it's coming up right under the middle of the more or less solid Pacific plate. And it tries to find its way out. That heat forces its way up through cracks, and there's quite a powerful magma plume coming up underneath the Hawaiian Islands, which is responsible for forming them. So what happens is that the rising plume periodically bursts its way out and has an enormous eruption and makes a new volcanic mountain. And if that volcanic mountain becomes tall enough to clear the level of the sea from the sea floor, then a new island is formed. And if the eruption keeps having new episodes, then it builds the mountain higher and higher and builds a bigger and bigger island. But of course the plate is moving along and changes its position, carrying those islands away from being directly above the rising hotspot, which is largely stationary, linked deep into the center of the Earth. And so next time it erupts, it'll start building a new mountain, a new volcano, and a new island. And so when we look at the direction of the plate movement, and we see that it's lined up with all of the chain of islands that form the Hawaiian Island group. And the most active and recently active volcano is right down at the big island of Hawaii, where we find Mauna Kea and the current eruptions. And then the smaller islands further to the northwest there are extinct volcanoes. They're no longer above the hotspot. And the seamounts that are shown right up to the end there are the oldest of the islands, where erosion has now erased the island back underneath the surface of the sea. So you can see that the biggest island is the youngest, and once the plate moves on, that volcano will become extinct. A new island will start to form at the head of the chain, and all of the others will gradually be eroded back down and disappear beneath the waves again. It's a fascinating process. So it all depends on the relative rate of eruption and the speed with which the plate moves. And those can be very episodic. The plate's not in a constant movement. It tends to shift at a varying speed. And of course, the eruptions are rather erratic as well. But this all begs the question, where does the heat come from? And it dates right back to the formation of the Earth, which of course is where the astronomy kicks in. So 4,500 million years ago, the Earth was formed out of material that was orbiting around in a huge cloud of gas and dust and dirty material that was surrounding the young sun. The sun formed at the center of this disk about 5,000 million years ago, and gradually then the leftover material started to gather under its own gravity in a disk that was spinning around the outside of the sun, and probably formed in the inner part of our solar system around about 200 small baby planetoids or planetesimals, little baby planets. And those baby planets would occasionally bump into each other and either merge if there was a nice, gentle, close approach where they were moving in the same direction and they just nudged up against each other, or if they hit head on, they would have a cataclysmic explosion and destroy each other and scatter their contents back around to float around in the remaining disk. But eventually things settled down, and we of course live on one of the four surviving predators of this process, that is the Earth, the others being Mercury, Venus and Mars, that swept up most of the material. Little bits of it still fall on the Earth. About 100 tons of space dust and little rock particles falls out of the sky every day and just makes the Earth that little bit heavier every day. And this is the leftovers of that formation process. But of course, this enormous bombardment of infalling material, all carrying a lot of energy with it, when it hits the baby planet, that energy is turned into heat. And so these small forming planets would have all been largely balls of molten rock. And the lighter molten layers of lightweight silicate rock will float to the surface, and the metals, the heavy metals, iron and nickel mostly, will sink to the center, being more dense, and form the iron cores of these growing planets. But all of that trapped an enormous amount of heat in the center of the planets. And gradually, as the bombardment calmed down, as the surviving objects had managed to sweep up most of the material, the outer layers will get a chance to cool off, being exposed to the cold of space. They could cool and form a crust. But still in the center, the material is red hot, was red hot, and still is today. But there is another factor, which is radioactivity. A lot of the material inside the Earth's core is still releasing energy today from radioactive materials like uranium and thorium, even potassium-40 that contaminates our bananas. Mind you, you'd have to eat 1 million bananas to really do yourself any harm, so don't worry about it. You might have other problems if you ate 1 million bananas. But anyway, the radioactivity of the early planets would have been much higher. A lot of short-lived radioactive isotopes would have been present, releasing their energy. Gradually, though, that decays away, but it generates a lot of heat that's still trapped in the center of the planet today. It's still trying to get out, and it's the volcanoes that are trying to bring that heat to the surface and allow the heat to escape to space. But if we look at other bodies, the question is, do we find volcanoes there? Well, here's a picture of our moon, and it's of course the side of the moon that is turned permanently towards the Earth. So it's the same side that we see all the time. As the moon moves around, it keeps one face pointing towards the Earth. And we see on the moon there the dark seas of the moon, the mare, as the Greeks called them, which translates as seas. They thought they looked very smooth and could possibly be filled with water or some other liquid. And they weren't too far wrong, because those large seas are in fact pretty much all circular when you look at them. And they really are just giant craters, huge impacts where other large space rocks hit the moon and punctured right through into the molten lava, molten magma beneath the surface of the moon, which flooded to the surface. Then we call it lava, and it would have flooded the resulting enormous craters and then cooled down and solidified. But that liquid lava is what's responsible for them having that rather smooth appearance. So the Greeks weren't entirely wrong. We also notice that the mare, the seas, are very dark. That's because material on the surface of the moon is constantly exposed to the solar wind coming from the sun. Lots of radioactive particles stream from the sun, high energy protons, all sorts of things, and they hit the surface and it gradually turns material darker. So where we see dark regions on the moon, they are old, they've been exposed to the solar wind for a very long time. The mare were mostly formed around about 3,800 to 4,000 million years ago, whereas the other lighter coloured regions are much younger material, and in particular we can see the impact crater at the bottom there, Tycho, very bright. That's one of the youngest features on the moon. It's only 107 million years old when a space rock smashed into the surface of the moon there and scattered material in every direction. You can see where the material ejected went almost all right the way around the moon in some of the rays that radiate out from it. Further up towards just above the center of the moon, there's a slightly older crater called Copernicus, and you can see it's mostly been a little bit darkened by that longer exposure of its ejected material to the solar wind. So it's gradually darkening down. So bright equals young, dark equals old on the surface of the moon. But all these craters, once upon a time, there was a big argument about whether they were volcanoes or, as I've been saying, impact craters. We now know that they're the results of space impacts. But even through into the 1960s, Sir Patrick Moore, in his books, refused to believe it. He was very much convinced they were all evidence of volcanoes on the moon. We do see some volcanoes. There's a few cone-shaped mountains in this image of part of the moon's surface here, handily pointed out by the black arrows. You can see the cone-shaped hills there that were volcanoes. They're now extinct, and of course you can see some obviously different looking impact craters next to them. They do look quite different, but this photograph has the advantage of being taken by the Lunar Reconnaissance Orbiter, which was orbiting around the moon only 60 miles above the surface of the moon there, so much better resolution than we could obtain even with telescopes from the Earth. Now if we move on from the moon and we look at the planet Mercury, actually it looks strikingly similar in some ways, apart from the fact that we don't have the puncture wounds that lead to the mare. We've got no huge dark seas on Mercury, but we do have lots and lots of craters covering a grey surface. If I showed you a zoomed in bit of Mercury and a zoomed in bit of the moon, it'd be really quite difficult to tell the difference. There are lots and lots of impact craters, but there are a few rather old and extinct volcanoes. Here's a picture of some volcanoes on Mercury. The ones at the left are much better showing, really, labelled there volcanic deposit. We've got a little heart-shaped volcano caldera, volcanic crater, and you can see where the bright material has recently, in astronomical terms, been erupted from that and deposited on the surface there. And again, features on Mercury gradually go darker due to exposure to the solar wind. It gets a great deal more solar wind, of course, being nearer to the sun. And so the surface really is quite dark. These pictures have had the brightness enhanced so we can see what's going on. So we do see evidence of volcanoes both on Mercury and the Moon, but they don't seem to be active today. And the reason is that their cores have cooled down. Rather like a child going out on a walk on a cold day with you, if neither of you have a coat, then the child will get very, very cold first and start to lose its core heat and suffer from exposure. So it's a very bad idea. You must make sure if you take a child out on a cold day, it's well wrapped up, because it will get and feel the cold much more quickly than you do. And that's because the amount of core heat inside a small object is much less compared to its ability to lose heat through its surface area. In mathematical terms, the Moon is a quarter of the size of the Earth in terms of diameter. It has a 16th of the Earth's surface area through which it loses heat to space, but only a 64th of the volume. So the amount of heat contained in that core is much less compared to the surface area. And so it's able to cool much more quickly, and in fact 4 times as quickly. And so within about 1 billion years, the Moon's core had more or less lost all of its heat to space. And that, of course, resulted in the volcanoes ceasing to erupt. Mercury's a little bit bigger. It's intermediate in size between the Moon and the Earth, probably twice the size of the Moon. And so it will have managed to retain that heat in the core correspondingly longer, and so has had volcanic activity on it more recently. But it's now pretty much solidified. Well, let's have a look at the next planet, Venus. This is the telescopic view that you get with the best telescopes we have. All they can see is the cloud tops of the atmosphere. Venus is about the same size as the Earth, just tiny little bit smaller, but essentially the twin of the Earth in terms of mass and diameter and so on. And so it would have trapped the same amount of heat inside it when it formed, and we would expect, therefore, to see the same volcanic processes. But this thick atmosphere means we just can't see what's going on beneath it. The atmosphere is 100 times as dense as that of our own, composed of carbon dioxide, has all sorts of other interesting chemicals like battery acid, sulfuric acid, which rains out onto the surface, and heavy metals that snow out onto the mountain tops. And really, it's Earth's evil twin. The temperature on the surface is 460 degrees. Here's a radar view. We can use radar to penetrate down through the clouds and see the surface of Venus. And what we're seeing here in the bright orange are some large impact craters. They don't look quite the same as impact craters on the Earth. They look a bit slumped. And the reason is that surface temperature is making the rock really quite squidgy. It's getting it up towards its melting point, just because of that 460 degree surface temperature. And the effect of that is that the rock is rather runny and just doesn't form the nice sharp crater rims that we see on Mercury or the Moon or craters on the Earth. We also don't see any small craters, and the reason is that no small space rock is going to enter Venus's atmosphere and do anything other than burn up before it reaches the ground, due to that 100 times density of the Earth's atmosphere. Any incoming space rock of any small size is going to burn up. Only the large ones make it to the ground. But what about volcanoes? Well, here's a marvelous picture of one of the 1,600 or so volcanoes that we see on the surface of Venus. Now, we think most of them seem to be extinct. We're not entirely sure. It's a little difficult to study what's going on. Again, we're using radar to see through the clouds here. And we can see that this is a classic shield type volcano like you see at Hawaii, therefore probably caused by a hot spot rising up and lots of molten lava running away down the slope there, the bright material. And it's very, very runny, of course, because of that high temperature. Again, it looks like the lava flows a very long way. Now, because there's no water lying on the surface of Venus, again, that incredibly high temperature prevents there being any oceans. It means that if there ever were any plates separating the different regions of the surface of the crust, then they're all dry, and so there's none of that difference in density. And indeed, there's no water to lubricate the process of one plate subducting underneath another. So we don't see any of that same process that we see on Earth that leads to the ash-type volcanoes going on. What we do see, though, is these weird pancake volcanoes. We don't really understand these. Again, they look like could be that the lava remains runny due to that very high surface temperature, and that could be somehow causing these weird shaped, very slumped volcanoes. So Venus rather different in some ways to what we see on Earth. What about the next planet? Well, here's a picture of Mars, and we've got the polar caps at the top, the dark regions, grey colour, and then the orangey, pinky, red, whatever colour you want to call it. Looks salmon pink through a telescope to me, but it is in fact a sort of rusty orange colour in this photograph of the rest of the desert regions. And then we have some white markings in the middle there. And those are ice clouds high in the Martian atmosphere. Mars's atmosphere is about 1% of that of the Earth's. So Venus is 100 times more than we on Earth, Mars 100 times less. But it's enough to support ice clouds high in the thin atmosphere there. And some of them are forming over the top of the tallest mountains. And the tallest mountains on Mars are in fact volcanoes. If we zoom in on that sort of left-hand equatorial region of the planet, we see a row of volcanoes and one large one off to the side there. This is the highland region called the Tharsis Plateau, and we see three big volcanoes in a nice straight line there with different size calderas, a few smaller volcanoes, one or two impact craters, and up at the top left there we see Olympus Mons, the largest volcano on Mars. In fact, it's the largest volcano in the solar system, and it's a Hawaiian type shield hotspot volcano being built up over many, many eruptions over millions of years, getting taller and taller, as if the hotspot had stayed in the same place underneath building one enormous volcano over time. And we think what might have happened is that the hotspot built those three that were in a line as the surface of Mars was moving over the top of the hotspot, just in the same way as the chain of Hawaiian Islands was formed on Earth, or is still forming on Earth. But then suddenly there's something jolted the surface of Mars and shifted it, and the hotspot ended up over underneath where Olympus Mons eventually grew, and more or less stayed in that same place for the rest of time until actually Mars ceased to have any volcanoes at all. So not only is Olympus Mons the largest volcano on Mars, but was the last one to be erupting as well, we think. It really is enormous. If we compare it to Mount Everest, the tallest mountain on the Earth, or to the big island of Hawaii, the Mauna Kea volcano, going from sea level, in the case of Mauna Kea, all the way up to the peak there, neither of them are even half the height of Olympus Mons, never mind the area. It's an absolutely enormous feature. And there we have a picture of it. If you placed it in the center of France, it would cover pretty much the whole of the country of France there. It's absolutely enormous. I just don't think we can imagine the size of it, really. If we look with the Mars Reconnaissance Orbiter, took a photograph down into the crater of the top of Olympus Mons, the caldera here. You can see there's been a number of different eruptions at different points, bigger ones and smaller ones. But look at those channels carved into the surface there of the upper levels. Those have been cut by water. So once upon a time, it rained into the crater, and then the rainwater cut channels, and then it fell down those enormous cliffs, filling a crater lake. Wouldn't that have been an amazing thing to have been able to see? But of course, Mars has dried out now. Now we can look at this diagram. It's a laser altitude map in false color, showing us the different heights of the different regions. So we've unfolded the entire surface, the two hemispheres of Mars here, and the deepest blue color is 8 kilometers below the average level, and then we come up through the blue into the greens and the yellows, which are more or less the average level of the surface, what we would use as sea level perhaps on Earth, but we have to use something as the reference point, so we use the average height here. And then we go up through the orange and to the red colors of the highlands, and you can see the red and the pink of the Tharsis Plateau, where those three volcanoes that we looked at earlier are lined up with their peaks going right up to being white for the highest points. And Olympus Mons there over to the top left at around about the 10 o'clock position on the clock face, off to the left of the three that are on the top of the plateau there. Now the deepest hole in the ground, the really deep blue feature over on the bottom right there, is called the Hellas Basin. And that's an enormous impact feature. A giant space rock crashed into Mars and punched an enormous hole in the ground, very much like one of the mare on the moon, perhaps. And it could well have been that impact that shifted the whole surface of Mars around and carried the hotspot to being underneath Olympus Mons. The other feature that's very prominent here is the enormous gash in the ground that runs roughly along the equator of Mars on the left-hand side there. That's Valles Marineris, the Grand Canyon of Mars, and it's enormous. It runs right from the top of the Tharsis Plateau, where there are lots of little box canyons there all feeding into it, and then down and out towards the right-hand side. And if you laid a diagram of that over the United States, it would run all the way from San Francisco to New York. The American Grand Canyon over there in the States is about the size of one of those little side channels that feeds into this thing. It's enormous. Now, just imagine that if you were able to use a time telescope to look back at Mars and see it as it was perhaps 3 billion years ago, you would have seen those volcanoes erupting. You would have seen rain clouds raining out water onto the Tharsis Plateau there, the highland regions, running down those channels, the side channels, carving them out, and then gushing down Valles Marineris in an enormous torrent, carrying all the water, carving that enormous channel and flowing back out through into the lowland regions, which are of course the northern sea, the northern ocean of Mars. We know this because if we look at the impact craters, which are mostly visible on the right-hand side on the yellow and orangey coloured regions of the mid-range terrain on Mars, there are loads and loads of impact craters there. That was land, and it's very old and has not been eroded to rub out all of those craters or filled in any other way, so they've accumulated over a very long period of time. If we look at the Tharsis region, where we have the volcanoes and the box canyons, a lot of erosion was happening there, a lot of eruptions from the volcanoes, pouring out new material and rubbing out older craters. And then the weather, rain, was carrying material along with the water down into the canyon, creating a lot of silt, and that would have silted up any small craters there as well. And of course dumped a lot of silt out into the sea, and the sea, the northern light blue coloured region, doesn't show any craters because that would have been silted up by all the material being washed down Valles Marineris and dumped out into the ocean there. If we look at the outflow region of Valles Marineris, you can see the braided river structure carrying out through into the Northern Ocean there, and we can see the effect of the shoreline. It's been enhanced here with older and younger shorelines where we can see how the seas on Mars gradually receded as the planet dried out. And so once upon a time, the planet probably would have looked something like this, with one huge continent at the bottom of the southern hemisphere, and perhaps an ice cap floating on the sea ice there on top of the great northern ocean of the planet Mars. So why did it lose all the water? Why did the seas recede? Well, Mars is a little bit small. It's half the size of the Earth, and it would have lost its heat out to space in the same way as the smaller planets that we talked about before and the moon. And eventually the volcanoes would stop erupting and the core would solidify as it cooled down. Now, once the core solidifies, you lose your magnetic field. It's the churning of the liquid metal inside the Earth that causes us to have our magnetic field. And just like in Star Trek, it's never a good idea to have your shields down. And so Mars would have lost its shields, lost its magnetic field, and then the solar wind would tear into the atmosphere. And what happens is that the water molecules, the H2O, gets stripped into H and O atoms, and the hydrogen, being very light, can escape from the gravity of Mars, which is not that strong because it's a smaller planet, and it's able to escape to space. So all of the hydrogen atoms are whisked away, carried away by the solar wind, and the oxygen is left behind. It's a bit heavier, and the oxygen reacts with the iron compounds in the crust of Mars and has created vast amounts of iron oxide or rust, which is why the continent's covered in that red dust. The red dust really is rust. And so really that's the whole story of the planet Mars, and just goes to show how important the whole volcanic cycle and the magnetic core of a planet can be to its habitability. Now we're going to move on out beyond Mars, and we find the asteroid belt, and we find the largest member of the asteroids, Ceres. We call it a dwarf planet now because it's large enough for its gravity to have pulled it into the most economical shape, a sphere. And so it's a 950 kilometer diameter little baby planet. You can see a picture of it there that was taken by the Dawn spacecraft as it approached, showing a lot of slightly soft looking craters and a couple of strange white spots. And down to the right hand side of the screen, we've got a picture of the Earth, the Moon and Ceres, just to give you a sense of scale. Ceres really quite tiny, even compared to the Moon there. But as the Dawn spacecraft zoomed in on Ceres, it gradually improved its resolution. We've got a colour photograph here, lots of craters that look like traditional impact craters, and those weird white spots again. So they organised a flyby, very low pass over the top of those white spots, and this is what the photograph showed. It looks like some material has been bursting through the surface and making these weird, complicated patterns of bright new material deposited on the surface. And it also looks like there are lots of cracks in the ground. And this is right in the center, remember, of a large crater that you could see. Here's a color image of the same region. And you can see actually it's a mountain pointing upwards, a conical shaped mountain. And this is an ice volcano. So it's a cryovolcano, a low temperature volcano. Nobody expected to find volcanoes on a small asteroid like Ceres, but here we have one. And here's a side-on view of another ice volcano that they discovered on the surface of this little asteroid. You can see lots of impact craters, but clearly there's a mountain made of ice that's been erupting from beneath the surface there. And we don't know if these are active today or not, but they certainly seem to have been active in the fairly recent past. Otherwise, again, that material would have been darkened by the solar wind, and it hasn't been. So what we think is happening with Ceres is that there is a rocky core deep in the center, and then that is covered by a mixture of water and ice at a warm enough temperature for some of that water to still be liquid. And then the outer crust is frozen ice with layers of dust and other material mixed in with it. That's why the craters are rather squidgy looking, is because they are made of ice, not rock, and ice is that bit softer, and so the craters have that rather soft appearance to them. And it looks like occasionally the surface gets cracked or punctured, and some of that water then bursts forth out and deposits minerals and salts and all sorts of interesting chemicals onto the surface. Now, the big mystery here is, why is the water not frozen up as ice right throughout this little dwarf planet? Why is there some residual heat inside such a small object? And we really don't understand that at all. The second half of this talk is going to take a look at what's happening out in the outer part of the solar system. But for the moment, I'm going to bring this talk to a halt and go and give my voice a little bit of a rest. And I'll see you for part 2.